I'll speak about, do you see what I see? It's about large-scale learning for multimodal videos. Today, videos are everywhere. We have large archives such as BBC and INA where TV channels are recorded. And even larger, for example, there are 30,000 hours of video uploaded to YouTube every hour. This is a large amount of videos. And similarly, there's 770 million surveillance cameras worldwide. So there's a large amount of video data available, and we want to understand and access it. One simple example for video understanding is the classification of activities, such as birthday party and grooming an example. These examples are from the multimodal event detection challenge. Another example is pedestrian detection and action recognition, which is important for car safety. If you are in a self-driving car, you want to detect pedestrians and determine if they want to cross the road or not. Another example is video surveillance. You want to watch people and see if there's anybody performing a suspicious activity and has to be stopped. A more complex task is the automatic description of a video. So here, the idea is to describe completely what's happening in the video. So here, for example, as the head waiter takes them to the table, they pass by the piano and the woman looks at Sam. Sam, with a conscious effort, keeps his eyes to the keyboard. And so as we can see here, this is not just about localizing one action or classifying a video clip. We really want to understand the content of the video. And in this case, we can make video a first-class searchable media. And so why do you want to use multimodal video representations? If you look at this example, we can see that the man is serving food to the woman, but only if we have access to the audio can we hear, is this Indian? And in this case, we know that the man is serving Indian food to the woman. So if we want to really understand the video content precisely, we have to have access to all the modalities simultaneously and use them jointly and train models to see and understand what's going on. Another reason for using multimodal video presentation is that it's a very rich source for large-scale cross-modal supervision. One problem in computer vision, and in particular video understanding, is the creation of manually annotated data sets. This is very costly, and in many cases, it's impossible to cover all the action classes automatically. So if we have access to this multimodal video representation, we can use it to create these cross-modal data sets. So for example, here, we can see the how to 1 million data set, where we have 100 million video clips. And for each video clip, we have used automatic speech recognition to transcribe the speech to text. So what we then have, we have clip pairs, which comes with narrations. And for these videos, here, these how-to videos are instruction videos. In many cases, people actually say what they're doing. So we do get a description of the content for free and can use this then for cross-modal supervision. In the following, I start by introducing the VideoBERT model, then present two recent approaches for cross-modal supervision, and in the end of my talk, introduce the very recent video vision transformer and future research. The idea of VideoBERT is to learn from multimodal videos. So as I said before, what we have the videos, the video clips with different shots, and the corresponding speech transcribed to text here. But in the meantime, you're just kind of moving around the cake around the board. So you really describe what is going on. This is the input to our model. And then we extend the BERT model to video and text, which allows us to learn the correspondence between video and speech. Furthermore, the BERT model has many parameters. And so we can learn from large-scale data here from cooking and instruction videos. First, a small overview over the BERT model. The BERT model has shown recently excellent performance for natural language understanding. The idea is to first pre-train a transformer model on large-scale text corpuses. So if we look at the illustration on the left, we can see that the input to the model is two sentences, A and B, and then they're fed into a transformer. And then to train the model, we mask out tokens and we mask out the correspondence between sentence pairs. This is used to train the transformer model on a large-scale unlabeled text data sets, and we can then fine-tune this model on downstream tasks, such as, for example, video text question answering on this quantitative data set. Then once we have this pre-trained model, we can fine-tune it on a small annotated data set for a specific task. And this model has shown to outperform most of the state-of-the-art approaches. And so now more in detail, what's in this model is the transformer architecture. So if you see here what this model takes as input, it takes as input a set of words. The words come into the model ordered as it is ordered by the sentence, right? And so the transformer model, what it does, it models self-attention between all the words or tokens in the input sequence. So if we look here, we have several layers. So the transformer model is built up by several layers. And at each layer, we model the interaction of each token with all the other tokens. And these transformer models are great for processing sequences. So initially, they have been used for text, so for natural language understanding, but more recently, they are also applied to images and videos. Videos in particular can be expressed as sequences of small clips, and recently images has been modeled as sequences of patches. Okay, and so basically what you have to take home message is that this transformer model rely on the self-attention between all tokens and are therefore more powerful than convolutional architectures where you only look at the input patterns locally. And then a bit more in detail, once we have the self-attention layer, on top of the self-attention layer, we have a feed-forward layer and layer norms and residuals which connect these different layers together. And one thing is important is the embedding and the positional encoding. So once you have the input, for example, an image patch, you have to have an embedding which projects this image patch to a token. And then in addition, you need to have positional encoding. Otherwise, the order of the words or the patches are not encoded. So basically, the input is this embedding plus the positional encoding, which goes into the transformer. And so now back to our VideoBERT model. So it extends the BERT model by taking as input the text transcribed with ASR and the video features. The video features here are modeled by 3D convolutions for small chunks of the video. So let's say we have a 1-minute video, we split it into 1-second clips, and for each 1-second clip, we extract 3D convolutions and we perform clustering to obtain tokens. And then once we have the input, the text and the video as input, we can use the same losses as in the BERT model, the masking loss and the correspondence loss to train our model. And now in more detail, the video representation, the video is represented by 2D convolutions for 1.5-second video clips, by 3D convolutions for 1.5-second video clips. And this outputs a 1000 dimensional feature vector for each clip. And the idea for 3D convolutions is to have convolutions in space and time. So you can see here in the illustration on the left that we have a small convolutional kernel, which is slided over the video clip. And then, as it's standard for 2D convolutions, we downsample and perform additional convolutions. And here we perform the 3D convolutions with the S3D operator, which are separable 3D convolutions. And in order to tokenize our video, we use hierarchical k-means clustering. So words are naturally discrete, and in order to make the continuous video discrete, we cluster the features into different clusters. And we can see here on the right, the centroids, you can really see that we have learned representative tokens of the different videos. Once we have set up this model, we can now train it. Here it's trained on 300,000 cooking videos. So cooking videos come, as I said before, in many cases with speech describing the content. So here, keep rolling tight and squeeze the air out to its side. Once we have trained the VideoBERT model, we can use it for 0.6 shot prediction. We take as input a previously unseen video and predict the corresponding verbs. Here on the right, the verb make and the noun pizza. The model has learned the correspondence between video and text. We can now also measure quantitatively performance for zero-shot prediction. The table on the left shows the results if we train 3D convolutions here as 3D in a supervised way, and below the results obtained for VideoBERT, which has only seen videos without any labels, so only video cooking videos without any labels and no correlation. And so here we can see that the performance of VideoBERT is comparable to the fully supervised performance. So this shows that VideoBERT learns the video language correspondence. And the table on the right shows the impact of the pre-training size. So we can see that the more videos we have for pre-training, so the first row uses 10,000 videos for pre-training and the last 300,000, and we can see that the performance increases significantly if we have more videos for pre-training. And we can see that the performance is also not yet saturated. So these models can really learn from this large amount of data. Another example where we fine-tune on a downstream task. So here we fine-tune for captioning on UCook2, and we can see again that our model outperforms the state-of-the-art on this captioning task. And so we can see here that if we just train the model on the downstream task, the performance is not as good as if you have this pre-training. And then an additional example, if we fine-tune for action recognition on exocentric cooking videos, we can actually see here that the performance drops. And what's the reason here? The reason here is this clustering, which is lossy. If you just want to learn the correspondence between video and language, the clustering is useful. But now, if you want to go into fine-grained action classification, the clustering actually hurts the performance. So here, if we look what's going on in more detail, the example on the top left and middle show actually the associated centroids, and we can actually see that we lose information which is important for classification. And so here we have next extended the training or visited the training objective of VideoBERT, and instead of masking out the clusters, we now model the features, the continuous features, and use contrastive noise estimation to learn these features. Alternatively, we could also use L2 loss to measure if the predicted features are similar to those which are masked out. What the contrastive loss does in addition, it takes into account the positive and the negative examples and learns by predicting positive examples and not predicting negative examples. And then on top of this visual and text model, we can have a cross-modal mutual information loss, where again, we differentiate between positive and negative pairs and can use those to fine-tune our visual features. And so then overall, the cost of our model is the language masking, LBERT, the masking of the visual features, and the cross-modal loss. If we now look at the results, we can see how this model performs for action prediction. So we have as input the temporal slice up to 1 second before the actual action, and then we want to anticipate the future. What we can see in the table is that if we increase the window size of the temporal interval before the action, we can actually see if we have a longer temporal window, we can actually see that the performance improves. This is nice as it shows that our model can learn long-range temporal dependencies. We can also show that it outperforms LSTM and average pooling. So average pooling, actually the performance decreases if the sequence is too long, because then we kind of average over too long sequences and smear out the information. LSTM improves a bit, and then our approach improves more significantly and outperforms LSTM on 3 different action prediction data sets. And if we look at the size of the visual model, what is interesting, so here we show the layers, the number of layers, evaluated with respect to the number of layers of our transformer. As we saw before, the transformer has the self-attentions and they're repeated over several layers, right? So for example, if we have 4 layers, 4 self-attentions are repeated 4 times. And then the attention heads repeat in space how often something is executed. So what we can see here is that we have the best results for 2 layers and 4 heads. And this is much smaller than what we have seen for language. And why is this actually the case? So the case, this is due here to the continuously pre-trained features, right? So we can take as input much more informative features than what we would have for language. And then again, if we ablate on the impact of the pre-training size, we can see that by having more larger data set, we increase the performance. And one thing is nice also that if we train on vision and language together, having the cross-modal information also improves the performance. So we have seen a first model which allows to model jointly video and text. It can be used for zero-shot prediction and pre-training and allows to model long-term temporal dependencies. However, it's restricted to instruction and cooking videos where the speech matches mostly the video. To get away from this restriction to instruction videos, we have introduced the approach speech to action. So here we want to apply our cross-modal learning to general movies. And so we want to infer, given the speech, what would be the corresponding action labels. And in many cases, the speech is unrelated to the visual content. So for instruction videos, it's related in most cases, but for movies, it's often unrelated. People often speak about actions in the past, actions that don't happen on the screen or in the future. And then there are many atomic actions like sit, stand, which occur frequently with all kinds of speech segments, and so they're not correlated. And so our approach learns when the speech is indicative of an action and which action it is likely to be. And so here, a brief overview. What we do is we train a speech-to-action classifier given movie scripts, movie screenplays, where we have scene descriptions and speech. And then we apply the speech-to-action classifier on a large set of unlabeled movies and obtain weak labels for these movies. In more detail, the movie screenplays contain both speech and scene descriptions from which we can then extract the actions. For example, here, agent number 1 hands him the phone. Peter says, "Hello, yes, operator, I accept the start charges." So this is an example where we can see from the scene description that somebody will answer the phone, and then we have the corresponding speech. The IMSB dataset supplies a large set of these movie screenplays, which we have used here. And then, as I said before, we can use the verbs in the scene description to determine the actions. And this allows us to obtain action speech pairs. So here, for example, answer phone, "Hello, yes, operator, I accept the charges," or "Thank you for calling so soon." Then we have this speech to action pairs for a large number of different actions. And we can then use this pair to train a speech to action classifier. So here we rely on the BERT model, which is pre-trained on Wikipedia to represent our speech, and then have an additional layer for speech to action classification, and our speech to action classifier then outputs the action classes. Once we have the speech to action classifier, we can see here a few results on a held out validation set. So here we see some likely speeches which corresponds to the label phone. So for example, "Hello, may I have the number? I ask you not to call. Hello, it's me." Or for dance, "Come on, we'll dance. Ladies and gentlemen, the first dance." And then for the class push, "Let go of me. You're standing strong. I can't even push you. Get out, get away from those." So you can really see that this speech is representative of the action. And we'll see that in most cases, if the speech is representative of the action, the label is correlated with the visual content. Not in all cases, but in the majority of cases. So now, once we have that, we can take a large set of movies and run the speech to action classifier over this large set of movies and obtain clips with weak labels. So for example, here, this clip would have the weak label answer phone. And at this stage, the text screenplays are no longer needed. So we've really learned this speech to action classifier from the screenplays, and we can now apply it to any movie and mine clips corresponding to the actions from these movies. Let's look at a few examples. Here, mine clips for run. You can see here, in all these examples, we have people running. And you can see here the different speeches which have allowed to classify these movie clips for running. So for example, he's running away, chase him, they ran into the woods. Another example, mind clips for phoning. "Hello, beep, phone beeping, Dad, are you here? Hey, it's me." So again, here we show all of the clips we show are correlated to the action phoning. And then here, examples for hit. So we can see on the bottom left an example for which the speech was classified into hit. But if we look at what the person is doing, she's actually performing a sports action, right? And so basically, backhand snap down, route off into the back was classified as hitting somebody, but in reality, it's a sport action. So this shows that our clips are weakly labeled. Not all of the labels are correct, but we have, as we'll see later, we have sufficient number of positive labels to be able to learn the action weakly supervised. Another example for driving. And here again, we can see that the example on the top right is incorrect. So here it's actually a police officer describing inside the station, he made a U-turn on an empty street. So to describe what the behavior was, and there is no correlation with the visual content, which would be car driving, and we don't see this here. So they're talking about something which is not visually seeable in the clip. And then if you look at the quantitative results, so the AVA dataset is one of the state-of-the-art datasets for action recognition. It has 1.6 million labels for 80 atomic action classes. It follows the long tail distribution of natural action distributions. So if you annotate movies with action labels, many of the actions don't appear often. So for example, things like sitting, standing appear very, very often, but then like swimming or jumping appear very rarely. And so this makes the training procedure harder. And so if you look at what our approach means, we have 2 orders of magnitude more examples for rare and mid classes. So you can really see for these classes for which we didn't have enough examples. So here on the bottom plot, we now have, and this is log scale, we have sufficiently more mined examples than we had originally, which for the annotated AVA training dataset. So for example, for point, we have very few annotations, and we can see that we have mined orders of magnitude more examples. Or similarly, for the action shoot, again, we have mined significantly more examples. And if we now train a visual classifier on these weakly labeled examples, here again, we use 3D convolutions to model the visual content, use a classifier to predict the action labels. Given these weakly supervised examples, we can see in the second line in blue, the S speech to action mined results. So we have no annotations whatsoever. Okay, and now if we compare the performance to the first row, where we use the fully supervised AVA annotations, we can actually see that in 8 out of 14 classes, we exceed fully supervised performance. So for example, if you look at drive, we have a 20% better AP with our mined examples than if we use the AVA training labels. And similarly for phone, again, we can see that we have 20% better performance. And now what the last row shows that if we use our model in combination with the trained examples, so here we use the trained examples to fine-tune the model trained with mined examples, we can see that this model outperforms both of the other ones in all cases. Finally, a fun example, we can also learn and mine abstract actions such as counting. So you can really see here that counting can appear in many different ways, counting pennies, counting paper bills, and so on. And another example is follow. Again, we can see that with our approach, we can learn abstract actions such as follow. And I'll now explain a second approach for cross-modal learning. So we've seen that we have this very rich information for movies, but now we see a second example where we can actually learn more sophisticated tasks such as video question answering, also with cross-modal supervision. So here we'll show that we can learn zero-shot video question answering with cross-modal supervision. And what is this question answering? So here we have a video clip. We have the question, what type of animal do we see? And the answer of our approach is fish. And if we had just access to the text only and trained on just some random text document, the answer would be stuffed animal. So I'll show a few examples later, but you can really see that this approach learns the correlation between the question, the video, and then the corresponding answer. And so how do we proceed to learn these answers automatically? So basically, if we have no annotations whatsoever, what do we do? So here the approach is, what we do is we generate a large-scale video question answering dataset automatically. And so the idea is, again, we start off with this how-to dataset, for which we have seen before that we have the ASR captions. We have the speech transcribed into captions. And then what we use here for cross-modal supervision, the previous part we have seen that we use the movie screenplays. And here what we use a textual question answering training corpus and the transformer model. And we then use the transformer to extract questions and answers from the ASR captions in more detail. So for text corpuses, there is the QA text corpus, which is quad V1. It comes with 100,000 question answer pairs for paragraphs from Wikipedia articles. So people, annotators, have taken paragraphs from Wikipedia articles and have annotated with question answer pairs. We can now learn a transformer which predicts the answer and the question based on this quad V1 dataset. So given this annotated text, we can then predict from the text the answer and the answer-aware question. We take this as input. The next step is we have our how to 1 million clips and the speech transcribed with ASR. What's important here is that we extract first the sentences. So the clips, just take random clips of 1.5 seconds and the transcribed scripts. We don't have a correspondence between videos and sentences. So the first thing here is to extract sentences and punctuations with a recurrent network. Once we have extracted the sentences, so here I'll put some pictures of him with another monkey, we then have also the corresponding video clip, which corresponds to the sentence, because the speech was extracted from the video. So now we know exactly at which point in the video the speech was happening. And so now we have these clips, these video clips, and the sentences corresponding to them. And we can now run on the sentences the answer extractor. So here, for example, we obtain monkey. And then given the sentence and the answer, we can generate the question. What animal did I put up pictures of him with? Okay, so then we have the answer and the question. Okay, and then this results in our how to VideoQA 69 million data set. So we take as input the 1.2 million videos from how to 1 million. On average, we obtain 43 video clips per video, and each one corresponds to a sentence. On average, the video clips are 11.1 seconds long and have 1.2 question pairs associated. And each question and answer are 8.7 and 1.2 words long. So in total, we obtain 69 million video question answer triplets. Here, a few examples. So on the top, you see the video clip, then next the ASR, add some of your favorite sprinkles, give it a mix. And then next we can see the generated question. What can you add to the mix? And the generated answer is sprinkles. You can actually see that this model trained on text only generates very relevant questions and answers for our visual clip. Another example, the sound is amazing on this piano. The generated question is, what kind of instrument is the sound of? And the generated answer is piano. And then the last example. So I've got 9 blobs of dough. how many blobs of dough are there? 9. This is actually quite nice, the question and the answer, which is generated automatically and corresponds very well to the visual content. And so one failure case. So for children, give one breath every 3 to 5 seconds. And then how long does it take for a child to take a breath? 3 to 5 seconds. This is clearly incorrect. So it hasn't generated the correct question and answer. And so here, obviously, this will not help for our training procedure. We have evaluated on average about half of our question answer pairs for the video clips are relevant. And so now, what architecture do we train to learn our video question answering model? So here on the left, we see the video and the question and then the answer. The video and the questions are embedded jointly with a multimodal transformer. We extract SVD features for the video, word tokens for the question, and then we combine them in our multimodal transformer. The answer is encoded with a separate BERT style model. And then what we use for training, we use contrastive loss. So here we cannot use classification loss because we have a very large set of different answers. So here we have actually 16 million different answers. And so in order to train this model, we not use contrastive loss. And what is contrastive loss? It takes into account positive and negative pairs. So we first have a video and the question and the correct answer, and then we balance the loss, as you can see in this equation, by a set of negatives to make sure that the video question representation and the answer representation for the positive pair is close and far away from the negative pairs. And so if you look at zero-shot VQA results, we don't use any annotated examples for training, but we show and evaluate results on state-of-the-art data sets and we use the test data only, for which we know the annotations and can evaluate if our prediction is correct. The top row shows random behavior. So if we don't know anything, but just predict randomly one of the possible answers in the data set. And then the line below shows the results for our model trained on the how-to VQA 69 million data set. And we can see that the performance for top 1 is good. And if you look at the top 10 best responses, we get it 50% of the time correct. And then a few results. So here the question, what is the man cutting? And our answer is pipe. And so we can see this was completely automatically learned, right, from this web data. So it's very good. And then one thing which is interesting is if you use text only. So if we don't have the visual learning in the loop, we can actually see the response would be onion. So I guess that's because people very often cut onions in this how-to videos. And here it's a pipe. So given that we have the video, we can predict the answer correctly as pipe. And another example, what is the largest object at the right of the man? It's a wheelbarrow. And if you use text only, it would be a statue. So basically, I guess people are in many cases visualized next to the statue. And here it's the wheelbarrow. So the wheelbarrow is recognized correctly in the video. And finally, what is the fruit shown in the end? So if you watch the video until the end, we can actually see that there's a watermelon appearing. And if we had the text only reply, it would be pineapple. And then finally, an incorrect reply. So here, in what room does the video take place? And the answer of our algorithm is dining room, whereas the correct one would be kitchen. So I guess the algorithm is for some reason confusing the two rooms. And if it was text only, it would predict studio. And then we can also use our approach not only for zero-shot prediction, but also for pre-training. So here, if we train our model only the second row on the training set, get the performance of 23 and 41. And then if we first pre-train on our how-to VQA dataset, we can see that the performance for the IVQA dataset improves by 12% and the other dataset for 5%. You can show that not only can our approach be used for zero-shot prediction, but also for pre-training. So we can use these large-scale datasets available online for pre-training. And then we can also evaluate the impact of the pre-training data set size, and we can see that for zero-shot learning and for fine-tuning, the larger the pre-training data set is, the better the performance. And we can also see that the performance is not yet saturated. And then very briefly, if we compare our approach to state-of-the-art approaches, we can actually see that in the fine-tuning scenario, it outperforms all the existing approaches, even if they use data for pre-training. This is because our data set is tailored explicitly for pre-training of VQA tasks. And so in conclusion, we have seen that weakly supervised learning exploits a large amount of data available online. It relies on the correlation between multiple modalities, here video and language. And open issues are how to scale it to general noisy data. So we've seen that the zero-shot performance is very good. However, it would be interesting to see how we can remove the noisy data to further improve the performance. And then it's also an open issue is how to balance different data sources and objectives. And in the last part of my talk, I'll show that these transformer architectures can also be extended to be categorize the video content. And so future work will be then to see how to combine these fully video vision transformers with multimodal information. And so here I just show how we can use this video vision transformer to encode the video information. So the idea here builds on the vision transformer ViVIT for static images, and we extend it to videos. So the idea, if you look at the illustration on the left, is we take a video clip as input, we embed it to tokens. I'll show in a minute different ways of doing so. Then we have the position embedding and the token embedding, and feed this into a transformer, and the classifier outputs the class label. So here it's for video classification. We want to classify and predict the class of a video. And in case of videos, we have a very large number of tokens. And so it's important to explore different alternatives, how to factorize the intention. I'll just briefly introduce the vision transformer ViVIT. This is a transformer architecture which has been applied to image classification. It takes as input 16 by 16 patches. So it splits the image into 16 by 16 patches and then orders them into a sequence and takes this sequence of image patches as input to the transformer. The image patches are linearly projected to embed them or flatten them, and then combined with the position embedding and taken as input to a transformer encoder. And then we can train this transformer encoder to predict the class labels. And here, to encode the video, the first most simple approach is uniform frame sampling. So we subsample the frames, and for each frame, we extract the 2D patches and concatenate the different 2D patches of the different frames which we have sampled. So effectively, we consider the video as a big image. However, this is not encoding optimally the video information. So the second approach which is better representing the video information, which is closer to 3D convolutions, we take as input, we extract first 3D spatial temporal doublets and project them linearly into tokens. And this already captures the temporal information in the tokenization stage, and it works better than uniform sampling. So here we extract these small doublets and then project them into linear embedding and use those as input to our video encoding. And now, if we take these patches as input to the transformer, and we have like a longer video sequence, we get many more patches and tokens than we would get for images. So now complexity is very large, right? So basically, it's called the complexity of the transformer is quadratic in the number of tokens. And if there are too many tokens, it's very slow and complex to train. So here we have two approaches. The first one where we train this fully transformer-based model. And the second one, which is a factorized encoder, where we first encode the doublets per frame and then have a temporal encoder on top, which encodes the relation between the different spatial transformer encoders. So we have this two-stage model, and the spatial encoder can also be initialized with a pre-trained ViD model. So here, this is similar to the lay distribution of spatial and temporal information. However, it's all trained end-to-end. And if you look at the comparison of the different model variants, the first model is the full spatial temporal transformer. We show results for Kinetics 400 and EpiKitchen. The second line is the Factorized encoder, and we can see that for Kinetics 400, we have a lot of data. The full model performs better, but for EpiKitchen, which is a smaller data set, actually the Factorized encoder performs better. And then the second advantage of the Factorized encoder is that it's much faster. So if you look at the runtime in the last column, we go down from 58 milliseconds to 70 milliseconds. And then one interesting thing is also, if for the model 2, we take average pooling baseline, so instead of modeling the temporal relations between the different spatial encodings, we can see that the performance drops significantly. So the two steps, spatial and the temporal encoding, really helps. And then what's important also is for these transformer architectures, it's important to have enough regularization, especially for smaller data sets such as EpiKitchen. And so here we can see the impact of the regularization with data augmentation, and also important is stochastic depth, that we stochastically drop out different layers of transformer. And you can see here on EpiKitchen, the regularization allows us a gain of 5.3%. And finally, if we compare our results to the state of the art, we can see that our transformer outperforms ViVIT. Transformer ViVIT outperforms the state of the art. You can see here. And then if we pre-train on an even larger data set, you can see that the performance goes up by a few percent. These are results on Kinetics 400, and similar results are obtained for Kinetics 600. Okay, so we have seen that with a fully transformer-based video encoder, we can obtain excellent results for action recognition. And so it's actually important to have models which take into account the spatial and temporal information. So here it is frame-based, but for future work, we could go even further and look at a region-based level. And so these are open issues, how to obtain better models. And here we would need more data for general actions. And so here this creates the link with the first part of my talk, where we have actually created all this additional data for these general actions. And so the next step would be to jointly train this fully end-to-end transformer model for video together with multimodal information. This is work which we're currently doing. And then another important issue more generally is confidence prediction, is to see how confident the predictions of a model are. And finally, what are future open research problems? So one thing which is important to go even further and learn even better models. So we have seen here that we can use the multimodal videos for learning. But one thing which would be also helpful to further improve the models is to interact with the world by embodied agents. And so not only have videos and text, but also to be able to interact with the world. And if you think of a child, if you put your child only in front of the TV, it might learn the correlations between the vision and the language, but it will not learn how to interact and move around the world. And so here, the idea is by interacting with the world to learn better visual representations, and of course also learn how to navigate and interact with the world. Learning can be done by demonstration and reinforcement learning, ideally with a combination of both. And one thing is actually interesting is how to leverage the large amount of data available online to facilitate this learning. So here, the example of the right actually shows, here we have queried for large amounts of additional rooms and houses to further improve the language, the visual language navigation in indoor environments. And then the example on the left shows a very recent transformer-based approach for vision language navigation. And here again, we show that these transformer architectures can help to further improve their performance. Thank you for your attention. Please let me know if you have questions.